Welcome to this other session preview. Both sessions are happening 2 days this afternoon. And today we'll be lucky to have Benjamin, Lucien, Kaminski to present the Automata and Complexity session. And then hopefully after Ralph Jung for the separation logic session. Thank you.
Yeah, thank you for the introduction. This is my first session preview, so let's see how this goes. And this session is about automata and complexity. I think you all know what an automaton is and also what complexity is. This is a rather diverse session. For the German speakers, it seems almost like some sort of Reste Rampe, but I'm always asked to chair such sessions, and I like it. So I will try to give such an overview about the individual papers and not so much about automata and complexity. Okay, so we have 4 papers, and I have put them in rather random order. Okay, the first paper is this, the complexity landscape of checking infinite descent. And what is this about? This paper is about cyclic proofs. And the cyclic proof, if you want to prove that such a formula XYZ, for instance, or a sequent or something like that is true, then you can construct a proof tree, and there you have some axioms, another inference rule, and so on. And then you have the same sequent occurring here again. And this is now a circular thing, and you might say that this is not a sound proof, but hello, hurry. But there are methods, so this is not necessarily sound, but there are methods to make this sound, yeah? And how to make this sound? You somehow have to ensure that from this bottom sequent to the top sequent, you still make some sort of progress. And this is called an infinite descent condition, even though it would seem like infinite descent would be something bad, but this is actually what makes the progress here. And this paper explores different criteria for checking such infinite descent and thus making progress within cyclic proofs and thus making them sound. Okay, the next paper is about efficient matching of regular expressions with look-around assertions. What are look-around assertions? This looks like this. You want to match this regular expression here, ABC star, but you want to provide some sort of context. Okay, so you want that ACB star is enclosed in some preceding AB, and some, I also wrote it here, and some BA that comes afterwards. Yeah, but you want to match this pattern in the middle. You just want to provide some context in which this pattern should appear. And this is what this paper is about. It provides a first formal semantics for look-around, for regular expressions with look-around, and this enables equational reasoning about them. Now, if you think, like me, oh, you can now do linear algebra with this, they already did it, kind of. But I think they don't have a full-fledged linear algebra, so there's still stuff to do in there. Yeah, go see their talk. And they provide a new algorithm for matching these regular expressions based on a new notion of what they call oracle NFAs. Yeah? So a new notion of automata, and the algorithm takes size of the regular expression times size of the input many steps. Right, then for our, for our third paper, this is about Parik's theorem made symbolic. So what is Parik's theorem? I don't really know much about this, so this is my personal take on the theorem. Let's say you have a word, W, and you project the word just to the number of A's and to the number of B's that occur in the word. Now, let's say you have just a binary alphabet. So what this really does is just, it takes a word and gives you a vector of counting the letters that appear in the word. And now the Parik theorem will tell you for every context-free language L, there exists also a regular language R, such that these are basically the same under this counting thing, which is quite remarkable. And this kind of means that by counting letters, you cannot distinguish regular from context-free languages. And moreover, this theorem also tells you that PL, so this counting thing from this context-free language and also from every regular language is expressible in Pressburger arithmetic. And now there's a problem. So this is apparently very useful in program verification, but the problem is the Pressburger formula, or the checking, I'm not entirely sure, is exponential in the alphabet size. But in reality, these alphabet sizes, like if you take UTF-8 or 16, the alphabet is huge. So this blows up in your face immediately. And one way to circumvent this is symbolic automata. And here the authors have provided such a Parikh theorem for symbolic automata. And with these symbolic automata, you can handle very, very large or even infinitely sized alphabet sizes. Okay, finally, the only paper which I know a little bit about, this is a positive almost sure termination, complexity and proof rules. Yeah, and this, what is positive almost sure termination? It speaks about termination of probabilistic programs. So if you have a probabilistic program, you can either say, well, it could terminate with probability 1, but here we are saying even more. We are saying the program terminates within finite expected time. This is a more stronger notion of probabilistic termination. So the program will terminate within finitely many steps in expectation. Okay, this is what positive almost sure termination is, and I, as my first thing that I did as a PhD, I showed that deciding this for probabilistic programs is sigma 2 hard in the arithmetical hierarchy. This is a hierarchy of more and more and more undecidable problems. All of them are undecidable except down here. This is the decidable problems. And then they get more and more and more undecidable. And this is somewhat high here. So this is strictly more difficult than deciding this for normal programs. But we thought, well, if you add non-determinism to the probabilistic programs, then it should be the same. But now the authors have shown there's another hierarchy that comes after these countably many levels are exhausted. There's another hierarchy on top called the analytical hierarchy of yet more undecidable problems. And the authors have shown that it sits at level, I believe, pi 1. So here, which is way, 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 way more undecidable if you have non-determinism in the probabilistic programs. All right, that's all the 4 papers in this session. Ralf Jung hasn't not appeared, I think. Yeah. If you have any questions, go to the session and ask the authors. Thank you.